Greetings everyone, I am Karan Ahuja, a fifth-year PhD student at the Human-Computer Interaction Institute of Carnegie Mellon University. Today, I'm going to talk to you about my work on CoolMoves, user motion accentuation in virtual reality. This work was done with my collaborators Eyal Ofek, Holz, Mark Gonzalez, and Andy Wilson at Microsoft Research. Virtual reality is a wonderful technology that enables a user to disconnect from the real environment and transform themselves into new and imaginative worlds. Here, the appearance of the user's avatar can be completely different from the real world. However, in this virtual world, our motions remain tightly coupled to our body. In this game, notice the difference between the avatar controlled by the user versus the computer-generated one. The computer-aided one is stylized and has a full range of motion, whereas the user in VR has only two motions, blocking and punching. This is quite different from the motions we are accustomed to in non-VR settings. In current PC and console game environments, avatars have a characteristic style associated with them. In FIFA, Ronaldo runs and kicks the ball in his unique character style. Similarly, in tennis, the motion is stylized for each character. However, current VR systems are bereft of such stylization and embellishment of the user's motion. Let's dive into why that is. The first reason is that unlike keyboards and controllers that have discrete button presses mapped to character motions, the motion in VR is continuous in nature. This continuous data stream is coming in at least 60 Hz, and the systems need to process it that fast to keep the VR experience real time. It is also paramount that the user should feel a sense of agency, that is control over their avatar, and a sense of embodiment, which is akin to body ownership. Thus, synchronization between the user and the avatar's motion profile is key. Furthermore, current consumer-grade VR systems track input from the user's headset and handheld controllers only. This severely limits the sense of embodiment of the user, as they cannot see themselves represented in the VR world. When full-body avatars are introduced without keeping the human motion dynamics in mind, it can lead to results that break the immersion as seen here. To alleviate this, inverse kinematics has been used to generate the untracked joints. This inherently limits the expressiveness and elegance of the avatar's range of motions to the tracked joints and the user's ability and skill. Many times we do not want the original motion. Users might want to feel like the avatar they are imbuing. Another key advantage of virtual reality is that it allows the user to manipulate large amount of objects in their vicinity. However, in real life, our physical spaces are constrained. In such limited spaces, we want our virtual avatars to expand our motion footprint. We also want to avoid fatigue over long VR sessions. Thus, it is beneficial to move away from this one-to-one mapping. A common approach that enables us to do this while maintaining embodiment and agency is to trick our proprioception. Prior research has found that the offset between the user's real and virtual hand can reach 14 centimeters before body ownership is reduced, and 21 centimeters before task performance degrades. This has enabled researchers to delve into haptic retargeting, remapping of the user's hands in VR, and scaling them as well. Building on such systems, we propose CoolMoves, a virtual reality system that processes motions from the headset and handheld controllers to synthesize expressive and elegant full-body motions for the user's avatar in real time, resembling those produced by expert performers while closely following the user's own input. Note that our task is different from pose reconstruction. As you can see in the external view here, the user's feet are stationary, but the ones produced by CoolMoves are accentuated based on the user's context. Utilizing existing motion capture datasets, CoolMoves generates the corresponding full body motion based on the user's input by comparing similar spatio-temporal motions with the nearest neighbor search and interpolating them using a weighted distance metric. Joint prediction probability is then used to temporally smooth the synthesized motion using human motion dynamics as a priori. Here is an example of the system in action when the user is dribbling a ball, is walking, or is climbing a ladder. From a very sparse search space, CoolMoves can map out motions that are spatially coherent and rotationally invariant, even though the exact motion may not even be in the search space as seen here. They are also temporally adaptive to the user's speed and motion direction, despite limited motion velocities in the search space. Here are what different motions will look like based on the activity context. Notice how the foot placement is different for different motions. This enables a variety of use cases. For example, using CoolMoves, we can generate full-body accentuated avatars. or social avatars that encode the affect and emotion of the user in their motions. CoolMoves can also help combat motion fatigue by scaling the user's motion to expand their overall footprint while preserving immersion and embodiment. Apart from scaling, CoolMoves can help in the remapping of limbs. For example, the user can make use of their hands to run while sitting on a chair. This capability can enable interesting accessibility applications for VR in the future. This wraps up my presentation. Thanks for watching. Please refer to the paper for full details.